Hello everyone and welcome to today's webinar, the Northern Tornadoes Project, identifying every tornado in Canada. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You have joined the presentation listening using your computer speaker system by default. If you prefer to join over the telephone, select the arrow next to the mute, unmute icon on the bottom of your Zoom screen. Select Leave Computer Audio and then select Phone Call and follow the prompt to dial in. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded and you'll receive a follow-up email next week with more information. And now I'd like to introduce Glenn McIlvery from ICLR. Glenn?
Thank you, Tracy. Good afternoon, everybody. Glenn McIlvery, Managing Director of the Institute for Catastrophic Loss Reduction. Thanks so much for taking part in this summer afternoon. We're very fortunate today to have with us Dr. Greg Kopp from Western University. Before I introduce him, though, I just wanted to note, talk about our next Friday Forum. That will be on Friday, August the 23rd, and the topic will be the business case for mitigation. Lower societal total cost of ownership. This gets into the whole issue of cost-benefit analysis for mitigation, whether it's worthwhile to put mitigation into place. I think you'll find it very interesting. So again, we're lucky to have Greg with us today. I've been with ICLR for almost 14 years. Greg is one of the first people I met when I joined the Institute. And he's a great guy. He's been affiliated with us for a long time. And I think you're in for a very interesting presentation. So with that, I'm going to hand it over to Greg. Take it away.
All right. Hi, everyone. I'm really glad you could join today. I'm happy to be talking about the newest project that we've been working on at Western with regard to the effects of severe storms on the built environment, and in this case, also in the natural environment. And so I'm going to talk about the Northern Tornadoes Project and really what we're doing with our, I'm going to say, aspirational goal of identifying every tornado in Canada and capturing meaningful data from it. To give a sense of where we started from, this is a map of Canada with all of the tornadoes between 1980 and 2009 that occurred. And one of the things that strikes you about the map isn't so much that we have lots of tornadoes in Canada, but you can see Canada is a big country and there's places where there don't appear to be any. And my colleague at Environment Canada at the time, he's now at Western, Dave Sills, has been looking at this issue, and we know we have thunderstorms in large parts of the country, and so we think that there's actually missing tornadoes in the country, in the region here highlighted in red. And so he led a study to try to see if we could assess how many tornadoes might occur in that region using some proxy data, essentially lightning data, mapped with population density and a few other indicators. And they came up with the idea that we're probably only seeing or identifying or verifying about a third of the tornadoes in Canada. And they published this work where they actually estimated that instead of the about 60 tornadoes that get verified each year, they could be over 200. They estimated around 230 tornadoes a year in the country. And so the question that we wanted to answer was, well, can we identify those missing tornadoes to see if this is real or not? And so that's where the idea for this project came about. And so we were fortunate in that a foundation that was interacting with the university, who is really interested in mitigating societal impacts, and we're really interested in tornadoes in particular, wanted to brainstorm ideas for a project. And so we've got this funding from a foundation called Impact WX, who is funding all the work that I'm showing here. And they have a big vision for what we're trying to do. And so we're trying to capture all of these tornadoes. So that's where this all started. We weren't quite sure how to identify tornadoes in places where there were no people. And this has not been really done before. And so the first thing we needed to do was figure out if we could do that. So what we set as our goals initially was, can we get these missing tornadoes identified? And to do that, we would have to improve our methods for detection of tornadoes and the damage that they leave. And the ultimate big picture goal of this is to really increase public awareness, improve building practices. As Glenn mentioned, I've been working with ICLR for a number of years, starting back really with the initiation of the Three Little Pigs project at the Insurance Research Lab for Better Homes. So we've been working in this space for quite a while of mitigation. And bringing in meteorologists, warnings, tornado warnings, and their accuracy and timeliness is also an issue. So we wanted to influence all of these kind of aspects as bigger picture goals. What I'm going to present today is the work of many people. This is the current team. Dr. Dave Sills joined us this spring from after 20 years with Environment Canada. In my opinion, he's the leading severe storms meteorologist in Canada, and we're really fortunate to get him to come and work on this project. And we have a team, though, that comprises both engineers and meteorologists, and also librarians. So on the team is Liz Sutherland. She's from library. She's helping us with the archiving of data. And then we have meteorologists and engineers. Some of these are doctoral students. Some of these have given talks in this venue in the past, particularly with the Dunrobin tornado last year and some others. So some of those faces should be familiar to you, but that's the team for this particular project. And I can tell you already, and as you'll see from the work I present, we need to actually grow this team to be able to capture all the tornadoes in the country, and we're working on that and expanding rapidly. So where we started from in 2017 was trying to figure out how we could actually identify tornadoes in regions where there was only forest and lakes in the boreal forest, say north of Lake Superior. That's a huge region. There's not many people there. It's difficult to get to. Many places you can't drive to, you can only fly to. And so our task was to figure out, can we do this? And if we can, how much is it going to cost to do it routinely? And so that's where we started from. So we use a variety of tools, and a partner from this on day one was Environment Canada, and we got their radar feeds. And in fact, we had a meteorologist embedded with Dave when he was still at Environment Canada. And we're using the radar to identify where possible tornadoes would happen. And we would look at really what the parent storms for tornadoes, which are supercell thunderstorms. And that's what we could track most easily with Environment Canada's radar. So we were using that to identify places where there was severe storms. And then we would use every other tool available to us to figure out what we could do. So damage reports and ground surveys, we've been doing this for a long time, and identifying damage. But again, in regions that have almost no population density, clearly that's not going to be the way to go. So we used two approaches. The first one then is really using satellite information. And as I think everyone should be aware, our Earth is being imaged continuously from space and elsewhere. And so we're actually able to get on a daily basis imagery from satellites. And so we could look at before and after imagery to see where tornado tracks would happen. So in the upper right, there is you can see in the middle under the red circle, there's regions where it looks kind of brownish, and that's a tornado path. And I'll talk more about that in detail. Then once we identify where there was a potential for a tornado, meaning there was some hint of damage, we would fly aircraft over. And so we found companies that make their living imaging trees in the north. We didn't know such a thing existed before, but we found them. And they can provide us detailed imagery with a very high resolution. So the satellite imagery available to us through public access has a resolution about 3 meters per pixel, and that's enough to see tornado damage path. What we wanted to do was be able to identify individual trees, and to the extent possible also the branches. And so that's what the aerial imagery provided for us, so that we could see individual trees. And The resolution that we had in 2017 was about 5 centimeters per pixel. Now we're operating around 2.5 centimeters per pixel, which is really quite amazing. You can see the branches in detail. You can identify the trees and the species very accurately from that. And the latest thing is drones, and this is actually transforming the way we're doing ground surveys, and I'll talk about that. But in northern regions, in the boreal forest, we can't get close enough to fly drones, and so we use aerial survey. So we have this combination of aerial survey and drones, as you'll see. The other, before we get into some of those details of the pilot study, I had on the first page our website, uwo.ca/NTP, and from there, we're trying to capture the public's ability to report tornadoes. Environment Canada, the storm prediction centers get calls when there's tornado, and people send them information. The Weather Network also receives a lot of information, and we've developed a portal as well to do that, so people can report tornadoes when we find them. And that's on our website, and that's only been live for about a month, but it's already becoming quite active. And one of the interesting parts is things like the Weather Network's meteorologists, they send storm chasers out. They're actually using our website to communicate with us. So we think this is going to be a good way of capturing damage and imagery in more populated areas where there's people, or if there's chasers out, they can report their information. We've also changed the way we survey data. We have developed an app for that, and the nice thing about that is actually live updates, and so our website will provide actually live information about where we're surveying and doing things. So we're really transforming the way we're gathering information for doing surveys. And all of this will be available on our website, and so open data is a big part of what we're trying to do. So we're going to be capturing, our aspirational goal is really to capture all the damage observations, all the data that we can get for every tornado. And so that's really the goal. And so we're working with libraries on archiving that permanently. So the current archive of Canadian data is based on just the intensity of the tornado is based on the most severe damage. It has a track length and a track width, and that's really about it. There's a little bit more, but not much more than that. And so we're trying to transform that database. Tornadoes are processes that evolve in nature, and so they change over time quite quickly. What they're going over also changes from grassland to trees to suburban areas with houses. And what we do is we identify all of the damage associated with that. And from that, we try to estimate the intensity. So for longer term research, we think it's really quite important to archive all of this data so that we have a better understanding of it going forward. I'm often asked whether there's climate impacts, and we just don't have enough information yet to say how climate change is affecting tornadoes, but we want to start capturing that data in detail so that we can assess those kind of things. So let's go to some of the data. So as I said, in 2017, we started this out. We didn't know how to do it, and so the goal of our first season was, let's see if we can identify tornadoes in a boreal forest, and it turns out we were able to do that. And we investigated 18 or many more events, but we identified 18 tornadoes, and of these we achieved archival quality geotagged aerial data. So we started to acquire data for the tree falls in the northern forest. Again, our goal was to identify tornadoes that were being missed, so that was one of the ways we're tracking the success of our project. And so in 2017, when we were focusing really just on Northern Ontario, we found 12 tornadoes, and we found 2 new ones that wouldn't have been found without that method, and we added significant data for 7 of the others. So we only added 2 in that process. I would note that on average, Ontario has about 12 tornadoes a year. So last year was, with that kind of number, it was a consistent kind of number. Quebec was interesting and has been interesting since we started this. There was a big outbreak in 2017, which I'll talk about in a few moments, but we found several new tornadoes there and of quite intense magnitude. And so we had quite a bit of success identifying new tornadoes in that region. And that included, as I said, the largest outbreak in the province's history and one of the largest in Canadian history. As we go forward, though, I think we're going to be realizing we're probably underestimating the number of outbreaks that are occurring in Canada, and this will have a big impact on risk modeling. So our first year was a success. We were able to develop a method. We were able to identify tornadoes in the remote areas, and we were able to acquire and archive that data. So our funder, our donor, was very happy with that and said, "Let's grow the project." And so 2018, we went to a larger kind of approach. So I just want to review then how we're identifying the tornadoes here. So we watch for the severe storms, and we use whatever data we can get from this. We use the National Weather Service Storm Prediction Center information. That's from Norman, Oklahoma. We use information from Environment Canada's storm prediction centers, and we use other information with the meteorologists on our team, particularly the work of Dave Sills, and he leads that effort. Then within the team, we communicate whether we think something's going to happen or not, so that our people doing ground surveys can be ready to move quickly. Then post-storm, we use the identified supercell tracks from the radar. We use satellite information, which gets updated daily. And we use damage reports as they come in from the various sources, including social media, Environment Canada, broadcast media, such as the Weather Network, and others. So we're using every kind of source from that. And then with that, we actually go out and look for that. And one of the challenges, as I mentioned, are the outbreaks, especially when we have many supercells to follow. And it's quite expensive to get the aerial imagery, and so we actually will fly airplanes over to see visually if there's damage or not. And I recall a day for an outbreak in northern Ontario. We wanted to see if there was damage or not, and one of my engineering students flew on a Cessna for the day with the doors open, and he said he only threw up twice. So it's a bit of a challenge, but to identify these, but that's how we're doing it. The satellite imagery over the last 2 years actually has improved quite a lot. So even in 2017, what we're able to get now in 2019 is significantly better. And so we're able to identify whether a tornado happened much more quickly. So that big outbreak in Quebec was again one of the most significant in Canadian history. You can see on the map where Montreal and Quebec City are, but there were 11 tornadoes that day that we identified. The most intense was we rated EF3, and that was based on damage to a cottage, a house, but a house that was quite thoroughly destroyed, but it wasn't built to, say, modern building code standards. Also, there were 4 EF2s, 5 EF1s, and 1 EF0. And so the bulk of these rankings is based, if you look at this map, it's not surprising to you, is based on tree fall. And so one of the things we're trying to better identify is how do we get intensity estimations from tree fall? And that's why we're acquiring this detailed data, because we believe we can find that in the patterns of the trees. So on that day, we used Environment Canada's radar, and these are tracks of 2 of the supercells as they translated along. And so from that imagery, we know roughly where the storms were tracking. And so we could map that out, and this is a map of those tracks. Using that, then we could look for satellites, and on the left is imagery from before, and on the right, imagery from after, and you can see the change in the landscape from it. You can also see in the image on the left, one of the big challenges for us is that there's clouds in the lower left of that image, and that's the kind of thing that has a big impact on us. Forest fires, too, with the smoke they cause, put a lot of haze into the imagery. That also causes a challenge for us. But from satellites, we're able to get a good idea of what's actually going on with the tornadoes. With that, we can then identify where we want to get detailed data, and we do the aerial surveys, hire the company to fly over and acquire those images for us at a much higher resolution. This is an example of it. This was the EF3 damage. So on the right, you can see we've outlined in red where all the tree fall damage was, and you can see why it's so clear in the satellite imagery. When you zoom in, you can see the individual trees, indeed the individual branches. And in the right side of that inset, the house that was destroyed simultaneously with those trees. So we captured that kind of imagery. This happened really early on in the project, and we actually didn't tell the airplane to take imagery in over the full track of this tornado. We only got a part of it, so we reflew it in winter. And so this is an image of the damage path that was taken in winter when there's snow on the ground. We didn't know if it would work or not. We thought that there's a chance often that we would be identifying tornadoes with snow on the ground. So we took this again as an opportunity to learn. And it was actually, we were surprised that you can identify tornado tracks even when there's some snow on the ground. It's probably a little hard to see on your screen, but in the lower right, you can see the individual trees that are down. You also have to be able to see the trees that are still up and how they're standing. And from that, we could identify the tornado track. And so this one was about 30 kilometers long and more than a kilometer wide, and got rated as an EF3 based on that house damage. How do we get that rating? You're going to see that it's really challenging currently, and this is an area where we're actively beginning research. So the way Environment Canada has rated tree damage in the path, they look at the proportion of the trees that are down in a particular area. So we identified the damage track. That's the yellow lines in the image. The center line of that damage is the red line. And what we do is we draw boxes around the damage. So the box size is the width, and then we make the length of the box to make them square. Also, is the length that same width. And so we have these boxes that way, and then we count the trees. And so this is labor-intensive effort at the moment, and it's how how my engineers are spending their winters now. They're counting down trees, which is not the optimal way of doing it. We've just begun working with a data scientist who works with artificial intelligence, and we're working on doing this with artificial intelligence algorithms. And so next year it should be, we expect or we hope that most of this is automated. So we have these boxes, we count the down trees, and then the proportion of trees down is related to the EF scale and the wind speeds. And so you can only get with this scale up to certain maximum wind speeds. And so the EF scale as it currently stands only allows for us to assess up to EF3 and nothing beyond. So if we had an EF5 tornado, the assumption is the damage would look the same. So we think that there is an opportunity when we look at individual trees and how they've fallen to get better estimates of the EF scale based on using some advanced modeling techniques, but we don't have those in place yet. We also, should be clear, is we're using both satellite and aircraft, and they give us slightly different answers. The aircraft allows us to see the detailed trees, and where the satellite imagery resolution doesn't. And so the damage paths from the aerial imagery are a bit wider typically than the satellite imagery. And we learned that partway along. And so we changed the way we actually did the flights in order to capture that data. One of the things, I think sometimes we think of tornadoes as being these monolithic things. An EF5 tornado in Joplin is a mile wide and however many miles long, let's say 100 miles long. And we think of it as being EF5 over that whole track. That's not actually how tornadoes work. Tornadoes, they vary in intensity along the track. They have a life cycle, so they start, they intensify, and eventually they diminish. So this track also shows the challenge with that, where we've identified trees in a fairly uniform environment. And you can see that we think we're calling this one tornado, but towards the ends, it starts to peter out, and the damage actually becomes intermittent. That doesn't mean the vortex has gone away. It just means that what's on the ground there, the wind isn't strong enough to break it, and so nothing breaks, even though the vortex might still be there. So that's how we're working with that. But this is again, this kind of detail I think is important ultimately to improve risk models for tornadoes. This kind of information can give us a much better handle of that. Again, the satellites, this is before and after imagery, and you can see that this is at an EF2 level. It's very, very clear in this image. We can work very well on paths. I had in the presentation some EF0 and EF1 damage, but I don't think you would have been able to see it on your screens at all. So that's one of the challenges for us. Weaker tornadoes, the whole basis for identifying tornadoes is the damage that they cause, and EF0 is by definition threshold of damage, and so it's really hard to see in imagery because you're just at the threshold. EF1, there should be imagery for it that you can see, and we are able to see it, but it's very hard for me to put that on a computer screen for you to see. So for EF2 and above, this method is fantastic. Below that, it's a challenge. You can see the track there with the red line and the track width with that. So that was 2017. That's where we started from. As I said, our partner wanted us to then, was excited by this result that we could do it, and then said, okay, let's do it. Wouldn't it be great if we could actually get this for all of Ontario and indeed all of the country? And so we said, hang on a minute, we can't jump that fast. So let's try to do this for all of Ontario and see if we can actually do it. And then if there's something significant across the country, we'll take a look and see what we can get. And I was particularly concerned with the prairies, and you'll see why in a few moments. So in 2018, we continued the pilot study. Our goal was to detect all EF1 and above tornadoes in Ontario, and again acquire library quality archival data for these. And so it was a busy year for us as we grew. We investigated 140 separate events, 114 of these in Ontario because that was our focus. We found 45 tornadoes across 5 provinces, from Saskatchewan all the way to a fairly significant tornado that occurred in New Brunswick. In Ontario, we found 23 tornadoes, and we found 15 new ones. And so what that means is, using the old methods, 2018, Environment Canada in the archive would have said there were 8 tornadoes, which would have been close to a normal year, which is about 12. We found 15 on top of that. And so we really increased by a substantial portion the tornadoes that were found. Quebec too, not considered to be a place of tornadoes. Environment Canada would have found 4, and we found 11. In fact, that number is still growing. One of the things that we found, we discovered an outbreak that no one knew anything about just in the past 2 months, of an outbreak of 8 tornadoes. There was no hint of damage. No one talked about it at all, and we found it solely from the satellite imagery. We were able to go back into the radar archive and verified the supercells for that day. And so even though we were looking, we weren't focusing on Quebec. It just indicates that stuff is happening out there and we don't quite know about it. And again, our goal is to find those. And then we had other provinces. We, of course, the Alonza tornado in northern Manitoba was the highest rated tornado in North America all of last year. We also think it was the highest rated tornado in all of the world. We're still trying to sort that out. It appears there might have been one in Brazil that was also EF4, but we're trying to sort that out. So anyways, it was a busy year for us, and we found all of these new tornadoes. So our methodology is clearly working. Adding to that, we were focused initially on the boreal forest and things like that, but even in the September 21st tornado outbreak in the Ottawa-Gatineau area, where the Dunrobin tornado occurred, we actually found a new tornado in a fairly suburban area that would not have been identified without these methods. So again, looking even where the people are, there's more tornadoes being discovered through this method. This is, I'm going to go now into some of the details. This is the Alonza damage path as seen from satellite imagery. The brownish color is due to the forest fires that were occurring west of there, and the smoke colored the image. But you can see the damage path. You can see the light, the yellow pin marks through the damage path, but you can see that path fairly clearly. This was an intense tornado, and there was a death associated with it, which was quite sad. And I think there was some other people that were quite lucky in terms of their surviving in the basements where they had foundations actually collapsed, but the bricks didn't fall on them. So we were lucky not to have more fatalities on this event, and I'm actually continuously amazed how few occur when you start looking at damage. This was the most severely damaged house. In the upper left is earlier satellite imagery that you Google Earth imagery. You can see the house structure on the left, and there are some other outbuildings and things. And then our photograph from a drone from straight above shows you what that site looked like several days later. And so this was a significant damage. House swept away. The trees all blown over. Lots of interesting things. A chest freezer went something like 800 meters, and so all sorts of crazy stuff kind of happens in these events, as you know. And so that's the most significant damage. And we do the usual structural damage of this. We rated it EF4, even though clearly this is a slab swept clean. The foundation details were, this was not a modern, well-constructed house. It had additions, it had foundation pieces that were just floor joists sitting on concrete and not fastened. So we went with an EF4 rating based on this structure. Dunrobin, September 21st. Of course, when you have a tornado in the nation's capital, that gets a lot of attention. We rated it EF3 based on the structural performance again, and this often relies now on how the walls are fastened to the foundation, and so we're working on that in detail in the lab and with modeling to get better understanding of house performance under these really significant winds. But this was a significant outbreak late in September. The lower image again shows aerial imagery. We did this later in the fall, and snow is already on the ground, and so this seems to be a recurring theme. Can we identify tornado damage in detail from that? You can also still see some blue tarps on people's roofs, even though it's a couple months after. So that event, there was 8 tornadoes, if my memory is right. And again, we used the detailed satellite imagery. We could contour the damage levels. We matched this with ground damage surveys, with drone information, and with aerial photography. The aerial photography, because Ottawa, has airports in the area. It was difficult to actually get aerial photography here, and so we're moving towards using drones for this kind of event to get the details that we want. So 2018, this is kind of a summary of it. We're starting to believe that that there's more tornadoes actually occurring, and we're starting to verify those, which was the goal of the project. And now we're in 2019 trying to do this for the whole country, and it's getting busy. So that's where we're going, and I'm going to talk a little bit about how we're using more advanced methods, particularly with drones. And so a little bit of detail on the map. So we can fly a drone over a site, and we have all the licenses in place to do that. It's reasonably challenging, but not that difficult to get the licenses. Basically, the drone will fly over. It takes photographs straight downwards, and then what you do is have to stitch them together. And up to a few years ago, that would have been a challenging research project, but now actually you can get a drone for about $1,000 and a controller for $600, and the software all comes with it to actually do this. And so it's amazingly inexpensive, although it is time consuming. So what we do is we identify the beginning and end points of the damage and the width of the damage. And if you look carefully at this map, you're going to see that it's a bunch of continuous lines, and we basically tell the drone, fly over this path and take images. And so we just systematically go back and forth, back and forth, back and forth. We change the batteries a bunch of times. This particular image is about 5 kilometers long and a few hundred meters wide, and took about 5 hours to traverse that. So it's time consuming. but it's relatively inexpensive compared to getting aerial flights. And with that, we can capture very detailed imagery. This is what, with GIS software, we can put that above. You can see the lighter green imagery, and I'm not going to zoom in on that, but you can see literally every branch when we zoom in. And so you get this very highly detailed information, which allows us to discover the damage. Recent work on this, the Meadow Lake event. So Meadow Lake and Cold Lake, Alberta, Meadow Lake, Saskatchewan. This is on the Alberta-Saskatchewan border. This kept us really busy earlier this spring, and there was an upgrade. We're currently investigating it. We think there might be up to 15 tornadoes there. I think currently we have 7 verified. This is the image on the screen is just a satellite image of one of the areas. You can see individual trees from it, and this is afterwards from a drone. And if you zoom in, you can see in great detail. This is the satellite image. You start to get blurry as you zoom in. This is the kind of imagery we now can produce. So we can see the downed trees, we can see the direction, we can see the root balls. If it's a root failure, we can see if it was a trunk failure. We can get those details. And so that's what we're using, and this is now transforming the way we're doing this work. And one of the reasons we want to go this route is in the prairies, there's a lot of areas where there's not trees. And so this is, again, the Alonza tornado. This is a view from a drone looking towards Lake Manitoba. You can see the tornado path really quite well from that kind of a view. And so we're trying to understand that better. The image in the left with the yellow circle is showing you roughly the equivalent path from straight above. What we want to do is figure out what's happening with the grasslands. And this is an area where there's nothing in the EF scale and we don't quite know what to do. So the satellite image on the left, you can see the damage path. The drone image on the right, again, you can see the damage. And as you go down to the ground, you can see, actually, if you were walking on the ground, you wouldn't say a tornado happened. The image on the right, obviously, is from the ground. There's some dead grass there. It was 3 or 4 days later. And we think that's actually what's causing us to see it from space. So the less resolution from above somehow shows us more clearly the damage path than on the ground. And so we think this combination is going to be important for us for getting at intensities in the prairies. But this is an area where we're going to be doing active research. And again, the use of drones is very useful in this regard. So this is, again, the Meadow Lake tornado. This is a drone image. There's I could zoom in and you can see those individual trees and branches on the image. And then the blue dots are where there was a ground survey. So this hit a campground. My understanding is something like 92 campers were wrecked or destroyed. And again, amazing that there weren't more injuries than there were. With this, campgrounds, I think, are dangerous places in tornadoes, and I wouldn't want to be camping during one. But we can put this all together in maps, and to get better ideas of the terrain, we're starting to use tools developed for the agricultural industry. So we can actually look at the colors that are going forward just from the imagery, and we process it to amplify certain things, and from that you can see damage to crops and things. So here's an image with trees again down. Here it is with the same kind of imagery, and you can see really clearly the direction of the trees and where the root bundles are. And so we think this kind of imagery and this kind of image processing is going to allow us to understand better the grasslands, but also to automate the damage. And so again, that's the direction we're going. So the source image is like this, just red, green, blue as a regular color, camera. And when we process it for simple agricultural tools, you can do this. So this, again, software exists in comes with the drones and the software that we use for analysis. It's quite amazing stuff that you can get off the shelf now. So we're working on that. Canada's a big country, and so we're working on identifying tornadoes across the country. It started quietly, but we are now busy with multiple events from Alberta to Quebec on a daily basis right now. I'm a little worried my team's getting exhausted and we have to work at managing that, but we are. and we're just keeping going on capturing this data. And so where are we at? Drones are clearly transforming what we're doing. Currently, we can only use them when we have road access. So we'll still use aerial surveys for places like the boreal forest, but in areas that are populated or that we can drive to, we're going to be using drones more and more. Again, there's challenges with this, dealing with especially the grassland on the prairies. There was again tornadoes last night in southern Alberta and southern Saskatchewan. They hit farms, and it looks like there was some ground scouring and things like that. So we're studying those kind of things in detail to see if we can get better intensity estimates. Right now, those go into the database as EF0. Nothing was damaged, and we think there's actually information there that can be captured so we can get a better handle of the risk of tornadoes. Water spouts are an interesting case. Again, in the north, there's trees and lakes, and a water spout is simply a tornado over water. And Environment Canada never had as its mandate to deal with marine issues. That's a different branch of government, and so water spouts aren't in the database. So we're working to capture those as well. This is going to be a challenge because obviously there's not damage over water, unless it hit a boat or something. So it requires photographic evidence. And so again, in unpopulated regions, that's going to be difficult to accomplish. We're using a lot of social media, and I think that's has a real strength. But as with all media-related things, that also has complicated some of our relationships, and we're working on building capacity there. The other thing that we're doing as part of this project, Environment Canada has upgraded their radar network to S-band, and they tune their weather radar for regular weather, not for tornadoes. And so we've actually acquired the Exeter radar. It was the research radar that Environment Canada had as a dual pole C-band, and we're going to be setting that up in the next couple of years. We have a 3D lightning mapping array from Environment Canada as well as portable weather stations. And so we're going to be implementing all of that hardware in southwestern Ontario to work on improved methods for identifying tornadoes from those tools. And again, that's a partnership with Environment Canada that we're working towards. So in the long run, we have a pretty big vision for this project. I think we want to be one of the viewed as a leading international center for tornado research with expertise on detection of tornadoes in remote regions. And the things that we're going to be working on, we're going to be doing these damage surveys, and we've already built the relationships with Environment Canada to do that. We're thinking beyond tornadoes to other convective storms as well, and thinking about things like hail and things which I know are of concern to the insurance industry. So we're working towards that. We want to collect all possible data because we think that in the long run will be what we need to better understand our climate and our risks, and that data will be open access.
Excuse me, Greg? Greg?
Yep.
Hi, it's Glenn. Sorry to interrupt. Are you safe right now? There is a tornado full-blown warning in London. There are tornado sirens going off on campus at Western. I'm not sure where you are, so I just want to ensure that you're safe and aware of this.
Okay.
This is not staged, everybody. This is actually happening right now.
Okay, I believe I'm safe. I'm in the engineering building quite far away from windows. Thanks for that heads up. I didn't actually hear the sirens, so that's interesting. I'm going to find out about that afterwards. Actually, this is the second time that happened. Last year, I was giving a lecture to high school students who were on campus at a lunch meeting, and they were on campus they were visiting various research labs, and the weather alarm went off actually, and we had a tornado warning during that as well. So, anyways, the campus takes it very seriously. Thanks for that, Glenn. Anyways, we want to automate all of this eventually. So this is a longer term goal, think 5 to 10 years out. But what I'd like to do is not have to have people looking at supercell tracks, looking at satellite imagery by eye. but by having artificial intelligent methods detecting these and categorizing them. And that's what we're working towards. And again, that's an aspirational goal for the longer term. And then part of the collaboration with Environment Canada to help them with their warnings using the hardware that we're getting and our observations from ground data to develop better tools for their forecasting work and for live updates. All right, and then of course for the insurance industry at Western, we've been working with you through ICLR for almost 20 years. And we want to utilize this data really to mitigate losses, to better assess risk, and to mitigate societal impacts of severe weather. That's of course our big picture goal. And I believe getting the best data we can and the best understanding we can of the risk is a really important factor. And so that's what we're working towards. So the takeaways for the insurance sector is there's a lot more tornadoes happening in the country than you might think. We're trying to capture information on that. We think that there's many more outbreaks that haven't been identified historically, and outbreaks are typically associated with the most intense tornadoes. You can have a one-off, you can get an EF5 by itself, but it's more likely on days when there's many other tornadoes. And so getting a better handle of the outbreaks is important, and I think what we're doing here will help with that. Developing the tools to get better intensity measures from trees going down will help us assess that risk also more realistically. And then we want to connect that with the things we're doing at the Insurance Research Lab for Better Homes and the mitigation efforts we're doing with that. So this should connect into all of that kind of work. So that's where we want to go with this project. So I'll stop there, and I'll be happy to take any questions. My contact information is there, and if you take a look at our website, any feedback on that would be great. But you can see what's happening with severe weather there. That's still a work in progress, as these things always are. But we hope that you can find that useful. So I'll stop there, Glenn.
Thanks, Greg. That was great. So we're going to open the floor to questions. If you have a question, please use the Q&A box at the bottom of your screen. We have our first question, and that is, have your studies exclusively focused on tornadoes from 2017 or later, or have older ones been investigated at any point during the project? If so, has there been any shift northwards where tornadoes occurred in the past and now?
So there's two questions in there. One of the things that we've seen is, and this makes some of our analysis quite complicated, is that we find there's trees down from other tornadoes that have happened in the past, and it seemed like a new tornado went over, and so we've had to differentiate new damage from old damage. We haven't done any kind of systematic post-analysis of where we've seen trees down. We would need an archive of radar data going back to do that as well, and we don't think that that's viable yet. So we haven't done a backwards analysis. To the other question about whether there's been a northward trend, we don't know. And I don't think we'll have the data. I don't think we'll have the data to answer that question for quite a while. Every time there's a change in methodology for identifying tornadoes, you get a change in the numbers. And so when radar was introduced in North America, the number of tornadoes identified went up. When with the introduction of cell phones, everyone has a camera on them now, numbers are going to go up. We've also changed this by systematically looking for tornadoes in places where they aren't, and so our numbers are going to go up. So we can't attribute that to a change in climate. We think getting this kind of systematic data over time will tell us those kind of trends, and at least will tell us what's happening right now. There's been analysis in the U.S. and there's still debate on whether tornadoes have been moving in the U.S. and there's some debate on that. I'm not going to get into that. The meteorologists, tend to think that in the U.S. There won't be a change in the number of tornadoes happening. There might be a reduction in the number of tornado days, which means that outbreaks may be worse. And when you query them, they tend to stop their assumptions at the 49th parallel. And when you ask above that, it looks like they expect that things may be worse in Canada. But I would say that conclusion yet is not definitive and is still an active part of research. So this is an area where a lot more research needs to be done.
Thanks for that, Greg. Here's my question, and you've kind of touched on it at the end, but why? Why does this matter? That's the thing. We don't want to just acquire data for the sake of acquiring data. We sometimes joke, if a tornado if a tornado happens in a forest, does anyone care? Is the kind of the question you might ask. And I think we should care. And the reason I think we should care is because we need to understand when and where tornadoes happen in this country. We need to understand their intensity. We need to understand when outbreaks are happening and get a better handle of that for modeling risk. My colleague Han-Ping Hong here at Western and I published a study of tornado risk in Southern Ontario several years ago. And to do that, we didn't have a good enough data set in Ontario, so we relied on Michigan, we relied on Ohio and Pennsylvania and upstate New York, so around the Great Lakes region, but they're on the other side of the lake. And the lakes, in simple terms, change everything. And so to get a better handle in Ontario here, we just need better data. And part of that is trying to capture everything if we're going to be able to assess that. Environment Canada has moved, they're responsible for warnings for the public. They haven't had a systematic study of what happens on the ground at all. So they will be out and respond when there's public interest. So if there's injuries, they'll go. If there's a big outbreak, they'll go. If there's media interest, they'll go and do a damage survey to verify. Often it's the same forecaster who made the call the night before that goes out and does the survey the next day. So there's a bit of a conflict of interest with that. I don't want to disparage them, but that's something that is a challenge. And so by getting systematic data, they will have ways to verify their warnings and see the things that they missed. I was talking with Dave Sills again this morning. We were looking at what was happening on the prairies yesterday, and we didn't think anything would really happen. But there was tornadoes, and we really don't have a good handle of predicting when tornadoes are going to happen for the warnings, even in our populated areas. So the more data we can get on this, we provide ground truth for the forecasters. We'll find better ways of predicting. We'll just improve that systematically. So for the Canadian public, there's going to be a benefit with that, with increased warnings and improvements. And for the insurance industry and the construction industry, we'll have better actual assessment of the risk so that we can better handle our infrastructure and the losses that are occurring around that. Great. So kind of on that same note, I know that your team was responsible for finding a missing tornado during the outbreak in Ottawa-Gatineau area. Of the others that you found, were any or many close to settlements, or were they all pretty isolated?
Which outbreak are you talking about?
Well, any of them 2017, 2018. Some of those missing tornadoes that you found, other than Ottawa-Gatineau, were they all isolated, or were some, fairly close to human settlements?
So like the June 2017 outbreak of 11 tornadoes in Quebec, my recollection is 4 or 5 of those were identified by damage because they were near small settlements, small towns, and so there was damage to housing and some other infrastructure, and so those got noted. I would say then that the rest of them weren't, but again, these are things that are affecting probabilities. And so one of the things that we want to do is identify where they're actually happening, get better identification of the intensity, and that allows, again, better risk models to be assessed. So even if they're not occurring where people are, I think it still affects our risk and our risk calculations. And so we need to look at that. Things like the electrical grid goes from the north, from hydroelectric dams in the north down to where the people are in the south, and then often into the US. And so those are things where getting a better handle of the risk is important, and those are not in populated areas. Those are in largely unpopulated areas. So there's a need for that kind of information, I believe.
Right. So just a reminder to everybody online, please use the Q&A box, the function at the bottom of your screen if you wish to ask a question. We've only had one asked so far, so please go ahead if you like. So Greg, you talked about better understanding the rating of a hurricane in a given box that you're looking at. So I think you said you can only really rate up to an EF3, and you were looking at the use of models to kind of improve your understanding of the rating. So if there was an EF4 or EF5, you'd be able to capture that. Can you expand on that at all?
Yes. So Alonza was a good example of that, where we had an EF4 rated tornado and we got the tree fall data. And so I have a colleague in the US who's been working with that. So he's developed a model that takes into account the strength of the trees, and then he applies a wind field model for the tornado. Basically think of a vortex, a swirling model, but that has that wind speed in it. And he identifies each of the trees and the direction that it's pointing. And from that, he is able to work out what the peak wind speeds are. And it's quite a complicated kind of model because it involves some fluid mechanics, some aerodynamics, and some geotechnical engineering. And you put all of that together, and you can get a better estimate of the wind speeds. And so he's actually, his preliminary work, which if this was a month later, I would have probably shown to you, but it's just not quite there yet. But he thinks he's got EF4 wind speeds from that. They used this analysis in Joplin. And so they went back and identified all the trees that were down in Joplin one by one. And then with Joplin, because it went over a community, there's also the damage caused to the houses simultaneously. And they correlated those two things. And so this kind of modeling, I believe, could work. To me, it's, you think of, I keep talking about Joplin, and that's a mile-wide tornado. It had a big impact. Had a huge impact, right? The loss of life is stunning, and the economic loss is stunning. We had in the Quebec outbreak, we have a couple of those tornadoes are a mile wide. And so with this method and identifying the trees, I think we can get a better handle of that. This will be controversial though. In Environment Canada, in the Quebec office, they didn't think you could get anything above an EF2 in Quebec, and we had a long argument just to make that EF3. If I'd showed you a photograph of the house, you said, well, why isn't that EF4 or 5, right? Well, we actually were there on the ground to look at the quality of the construction, so EF3 was our best rating of it. But the tornado could have been above that. We just can't say that from how the damage went. And so looking at the particular tree faults, the patterns, we can do that. But this takes quite a bit of, it's still in the research realm, but we're getting close with that. I think a year from now, we should be able to show some post-analysis of some of these tornadoes that we do have to see what we think they were. We need to do more work too and find out what the capacity of those trees are. So we need to send people to the north and have them go and pull down trees in those areas just to see how strong they are, because we don't have a good handle of that yet either. So there's a lot of moving parts to get this done, but that's what we're working towards.
Thanks. We have another question online here. Is there a risk of an increase in tornadoes in Western Canada?
The meteorologists, the climate scientists that I talked to would give a hesitant yes to that, but we're not, it's not a definitive conclusion. And our data, since we're systematically trying to capture more data, we're likely to capture more data. And so our work won't be able to give that indication until our methodology is set and then we have multiple years of data. There's also large-scale cycles in the atmosphere. It seems with tornadoes, there's something that happens on a 20-year cycle, and so separating that out is also very, very difficult. I don't think we're going to get a good answer to that question for 20 or 30 years unless the climate scientists can do something that, once the climate scientists start to be able to resolve thunderstorms accurately with the climate models, maybe then we can say something. But at this point in time, we just can't say anything.
Okay. I was at a hail conference last year, heavy on the meteorology, and some of the models are indicating that some of the Cape models are looking at Cape, which is the convective available potential energy that's, you know, connected with thunderstorms. The models are showing that there's going to be higher potential for Cape in the north, moving to the north and to the west, and so there's going to be less hail in places like Florida and more hail up in Western Canada, Central Canada. So, I mean, where you get hail, you get thunderstorms, you get lightning, you get tornadoes. So it's a dotted line. It's not a direct line, but we could. Some of the models are indicating that we're going to see more convective storm in the north and the west.
Yeah, and that doesn't surprise me, but we just can't prove that yet, and so we want to be careful with the conclusions that we do make.
Right. Can you tell us a little bit more about the Exeter radar? Is that being dismantled and moved to a western property, or is it remaining where it is, or what's going on with that?
Yeah, it has been dismantled. It's on western property in boxes, and I'm looking for, I'm working on finding financial support to set that up somewhere in southwestern Ontario. Windsor has always been kind of a black spot for radar in Canada, and we rely on Detroit for that. Tornado Alley curls through Michigan, Detroit, Windsor up the 401, and we would like to cover that area. So we have that radar, and I'm looking for financial support grants or otherwise to start to get that operational here. That we need staff for that as well, but that's what we're working towards. The S-band, I don't know if you look at radar and you go to Environment Canada's website, it has that contingency thing. The S-band radar isn't up and running there as far as I know. But the reason there's no radar there right now is the C-band is sitting in the Insurance Research Lab for Better Homes in crates.
Interesting. Well, I think that wraps it up. I don't have any other questions online unless anybody does. If you can type them in within the next couple of seconds. But Greg, I really want to thank you for taking a summer day to do this for us. We really appreciate it. We had a good turnout online. This recording will be up on our YouTube channel within the next few days. The slides will be on our website within the next few days as well. Also tune in Friday, August 23rd to learn about cost-benefit analysis for mitigation. I think that's about it. So Greg, thanks again. Really appreciate it, and good luck on your research, and we'll keep in touch.
Thanks, Glenn. It was a pleasure.